Hello and welcome to episode 9 of this series, and today's perfume is Joy by Jean Patou, which was created by a perfumer called Henri Almeras in 1929, so the year of the great stock market crash. And since then, until recently, was considered the greatest floral perfume ever made, and I would tend to agree. It's absolutely magnificent combination of expensive florals, Bulgarian rose, everything in there is top-notch, absolutely top-notch. Amazingly, the parent company of Christian Dior, LVMH, bought Jean Patou perfumes recently, and they discontinued Joy. And the reason they discontinued it is simply that they wanted to bring out a perfume called Joy in the Christian Dior range, which I think is, first of all, completely ridiculous, because Joy is Jean Patou, and secondly, why discontinue a perfume for that reason? Not only a perfume, but probably the most famous perfume in 20th century fragrance. Anyway, this is the way of business, and it's a very sad way. But you can still buy Joy in secondhand or sometimes in old perfumeries. It's not cheap. In fact, it used to be the most expensive perfume in the world. I don't think that's the case anymore. But anyway, it's beautiful, and sadly, they've killed it. Okay, so today I'm going to talk about how to test the vibrational theory experimentally. And I have explained that one way of testing it is to change the vibrations of a molecule, of course, if you can, without changing the shape, if you can. And just about the only way to do that properly is to replace hydrogens in a molecule, of which there are usually plenty. Every carbon is decorated with hydrogens. Replace if you can, every hydrogen with a heavier hydrogen called deuterium. Let's take the example of hydrogen and deuterium. Hydrogen is the simplest element in the periodic table, and it has in the center of the atom a positively charged particle, the proton, and around it one electron that goes around. You can add a neutron to the nucleus, and the neutron, as its name indicates, has no charge. So what you're adding is just weight. You're going from basically 1 to 2 in weight. And the fact that there is a neutron in there is almost invisible from the outside, because chemistry is really the science of the behavior of electrons, not so much nuclei. And therefore, when you compare hydrogen and deuterium, they have similar properties. Not exactly identical, but fairly similar, because the neutron has relatively little influence on the way the electrons behave. So what happens when you replace hydrogen with deuterium in a molecule? Well, the answer is not that much, because the chemistry will be rather similar, but of course the weight will be heavier. And the main thing that happens is the vibrations are different, because each vibration is determined by the relationship between the spring constant, which is the bond between the atoms, and the masses. So if you change the mass of hydrogen from 1 to 2, then the vibrations will go down by a factor of 0.7, roughly. So you go from, let's say, 1,000 wave numbers to 700 wave numbers. If they have different vibrations, they should smell different. So how do you get hold of smelly molecules, odorants, that have deuterium in them? That was a big problem in the beginning, because people don't normally make molecules with deuterium. They have no need for them. So, for example, if you look at a chemical catalog, a normal chemical catalog, they have relatively few deuterated molecules in them. And all the ones they have are meant to be used in one very particular situation, which is nuclear magnetic resonance. That means the range of molecules that you can buy, or that you could buy, was rather small. And many of those were rather weak odorants or not particularly interesting from a smell point of view, etc. So when I first started doing this, I selected one which was a well-known odorant. It's called acetophenone. And it basically smells of hawthorn. It's not a very nice smell. It's sort of oily, floral, sweet smell. And you could buy deuterated acetophenone. So I ordered some, and it came through the mail. And when I smelt it on a smelling strip, it smelled rather different than acetophenone. But you could tell while smelling it that initially there was a difference. On first sniff there was a clear difference, and then it sort of gradually went away. And part of the problem with acetophenone is that you get used to it. You desensitize. This happens often with certain odorants, typically the smell of violets, ionones, and acetophenone. Let's say you buy deuterated and normal acetophenone from a chemical supplier, and you smell them both. If there is a smell difference, it could be due to some small amount of an impurity which is present in one but not the other. And the reason it's present in one and not the other is because they haven't been made by the same method, or even sometimes just the same day, that there's something slightly different. The nose is very good at picking up small differences. So it was very important to put the acetophenones through the gas chromatograph and smell them as a single peak without impurities. A gas chromatograph is, in principle, an extremely simple instrument. It consists of a tube, a spiral tube, very thin tubing, all coiled up. So if you uncoiled it, it would be like 40 or 50 meters. And that tube is inside an oven, which is kept at a constant temperature. And through that tube is flowing a gas. And what you do is you inject the sample into the tube at one end, and the sample travels through the tube, pushed by the gas. But it's a bit more complicated than that, because the walls of the tube are sticky. So if you have a molecule which is very sticky to the walls, it'll take a long time to come out, because it'll spend most of its time sticking to the wall. Then it gets off the wall and moves along with the gas. Then it goes back on the wall and then comes off the wall again. So you can easily imagine that you can separate molecules in this way. So the idea of the gas chromatograph is that every molecule spends the same amount of time flowing with the gas, but a rather different amount of time sticking to the wall. So a gas chromatograph enables you to do something really rather wonderful, which is to separate molecules. If you inject not one molecule, but a mixture, the mixture goes into the tube, and then each molecule in the mixture sticks to the walls, or flows along with the gas, or sticks to the wall and flows at with a different time. So some of them stick more to the walls of the tube and therefore come out later, and some stick not at all and therefore come out first. And that's called separation. And that gives you peaks in the readout. Anyway, so you can also add a wonderful thing to a gas chromatograph, which is at the end of the column, instead of putting it through a chemical electronic detector of molecules, you can put it through a pretty good detector, which is your nose. So you have a tube coming out, and you simply smell what comes out. And that's called GC smelling. And then when you put your nose on this thing and the peaks come out, you can smell them. So I asked this company called Quest, which had its headquarters only an hour away from London, whether I could come and bring the deuterated and normal acetophenone and put them through their smelling GC to see whether they smelled any different. So I went to Quest, and their chief technician very kindly agreed to do this with me. We went down to the chromatography room, and of course he was a very senior chemical technician. He was in his 60s. He'd smelt more molecules than I've had hot dinners. So we put in the deuterated acetophenone in the machine, and he said, I don't even need to put in the normal one. I know what it smells of in the GC. So he put in the deuterated acetophenone, and after about 2 or 3 minutes, it came out of the column and he was smelling. And he turned to me and said, "That doesn't smell of acetophenone. I know what acetophenone smells like." Anyway, we leave the GC room and we go upstairs, and he tells the head of chemistry at fragrance chemistry at Quest, "You know, this acetophenone smells different. The deuterium acetophenone smells different." And the chemist says, "Really?" Picks up a smelling strip, dips it in the deuterated, and I could see his surprise on his face. And then he just put it down and said nothing much. And so I left and went back to London. Anyway, I put this result in the paper and stated that the acetophenone smelled different. What happened next was that a US group that worked on olfaction repeated the experiment with naive subjects and had them smell acetophenone and deuterated acetophenone. And they found no significant difference, which did not really surprise me because, first of all, it's better done at very small concentrations, and secondly, naive subjects aren't very good at telling differences between smells anyway, usually. So we needed to rethink this. In the case of acetophenone, we only had 8 hydrogens. And if one assumes, which is not impossible, that the difference perceived by the nose between hydrogen and deuterium will get stronger when you have more hydrogens, then 8 maybe wasn't enough to produce a really good, strong effect. And at the time, I was working in Greece. 2 things happened virtually simultaneously. One was that I made contact with a local fragrance firm called Viewpoint, small but absolutely scientifically excellent, with a very good chemistry lab, tremendously competent chief chemist, and basically a company that's interested in research and development. And then I discovered that in the intervening time between the acetophenone experiments and then, a method had been developed that would enable you to put deuterium on any molecule you like, pretty much. And the way this works is you take a molecule that's full of hydrogens, you put it in deuterated water, which is cheap and plentiful, and you increase the temperature to about 120 or something, not very high, 120 degrees, and you drop in a catalyst. So it's a special powder made of rhodium, and for reasons that I don't even understand, I don't want to go into, the rhodium enables the exchange of hydrogen with deuterium. So the molecule comes along, and in time, because there's lots of deuterium around in the water, each hydrogen on the molecule gets exchanged by the catalyst. It doesn't happen without it, with deuterium. At the end of this couple of hours of reaction, you have essentially 95-98% deuterated whatever it is that you put in. So given that we wanted the maximum number of hydrogens to be deuterated, we decided to use the largest possible odorants. And these were macrocyclic musks. So what did we do? We ordered 10 grams or so of the 15 carbon ring from a company called perfume in Switzerland. And then we deuterated it almost completely. So when you deuterate a 15 carbon musk, you have 28 hydrogens that can exchange for deuterium. And at the end of the reaction, it's not like every molecule has had every hydrogen replaced by deuterium. There's a spectrum. Some of them have 28, and most of them are around 24, 25, 26, and then there's a few that are less than that. It's a random process to some extent. So having figured out the method for deuteration, which is this very clever method with a catalyst, I asked the chief chemist at Viewpoint whether he would be interested in trying it out and seeing whether the musk smelled different. His name is Dimitris Georgianakis, and he memorably said, yeah, sure, let's try it. So I bought the little pressure vessel and the deuterated water, and we brought them to Vioril, which is situated just outside Athens. And I was there with my graduate student, Cleo Magnati, who was working on this full-time, essentially. And after a week or two, he said, come and smell the results. And so we asked him, what does it smell of? And he said, I don't want to say. You have to come and smell it for yourself. I don't want to say anything. So you can imagine, Cleo and I were both pretty nervous. Anyway, we got in the car, we went to Vioril. Dimitris brought out the little vessel in which he had collected the fully deuterated musk. And at that point, I did something that I thought was pretty heroic for me, which is I decided to take photographs of the event with my little camera instead of smelling it. I wanted to see their faces, and in particular Cleo's face, because she was very familiar with the smell of the undeutrated musk. I wanted to see her face when she smelt the deuterated one. She's now become a perfumer, actually. She has a really good nose. And then Cleo opened the little vessel and smelt it. And her face lit up. Her face just lit up. She was beaming because it smelled completely different. I've said before that actually smelling a bulk compound like that is kind of meaningless because it could in principle, contain impurities or some very powerful, nasty stuff that would obscure the smell of musks. So what we had to do was to do the gas chromatography smelling part so that we would smell the peak of the musk pure. And at that point, we contacted Simon Gain, who'd been toiling away for months on the acetophenone experiment. So we went to London, and he had the GC smelling equipment installed in his lab, and he also had the help of an extremely experienced technician called Ian Smith. So at this point, we were helped by a stroke of luck. A few years earlier, a graduate student called Christina Zilano in the US had developed a simple technique for capturing peaks that come out of the GC in a small plastic vial, a plastic tube called an Eppendorf tube, and having the GC peak, the stuff that comes out of the column, just go into the tube, and then you shut the tube, and it stays in there and sticks to the walls because it's polyethylene. So in this way, she could capture any peak coming out of a GC, and then it was easy at that point to open the tube and smell the thing, and you could smell it for as long as you liked. I mean, it wouldn't last for an hour, but it certainly would last long enough for you to get a good feeling for what the smell was. And this seemed to be good enough for naive subjects, for untrained subjects. It turned out that naive subjects were perfectly good at detecting the difference between pure, GC pure, deuterated musk and non-deuterated musk. And this was the story of how we established really that human olfaction can tell molecules apart from vibration.